Example problem. A 0.096 meter diameter circular coil of wire with 50 loops is in a 1.1 Tesla magnetic field. If the loop is removed from the field in 1.5 seconds, what's the induced EMF in the wire? In what direction is the induced magnetic field? And in what direction is the induced current? So the first thing we want to do, I think is going to be helpful, is to draw a diagram of what's going on. So the diagram we have is going to look something like this. We have a circular coil of wire that's in a 1 Tesla magnetic field. Okay, so here's my loops of wires. I'm obviously not going to draw 50 loops. But here's my loop of wire, and then I have a magnetic field that's traveling through it. Now, I wasn't specific on the direction, and for this problem, the direction itself is not super important of the field. I'm just drawing mine to the right. What is important is that it's going perpendicular through. Unless I tell you otherwise, assume that. So then what's going to happen is we're going to remove the loop from the field. We're going to pull it out. Okay? So we're going to take the field. The field's traveling through this way. We're going to pull the loops out. So what's going to happen is I'm going to decrease my field flux, which we'll show that here in just a second. So the equation that we're going to use is Faraday's law. Faraday's law is EMF equals negative N A delta B. Huh?
EMF is the purple arrow?
No, this is just the motion of the wire. So I'm pulling the wire through the field. It could be the field is going through. It just needs to show some change. In this case, the change is the coils moving. I'll show you what that has to do in here in a second. So the numbers and things that are given. We have a diameter for the circular coil. Why did I make it diameter? I don't know why I made it diameter. Whatever. Normally I'll give it to you as a radius. It's not a huge deal. So we have the diameter given to be 0.096. It does need to be in meters. I gave it to you in meters. If I give it to you in centimeters, just convert it. I have the number of loops to be 50. I have the magnetic field to be 1.1. The time interval, how quickly it's changed, is 1.5 seconds. And I want to know what is the EMF. Okay, so we need to start trying to figure out how to plug things in, where to put everything. And that can sometimes be a little tricky, so we're just going to go a little bit at a time. So we're going to start with the EMF. That's what I'm solving for, so I just write that. Negative N. So N is the number of loops, so that's 50. All right, now we get to A. So area is the area of the loop. So this is a circular loop. So the area of a wire is normally 2 pi r. Since we're given the diameter instead, it's just pi d. So pi times 0.096. Oh, yeah, thank you. I'm thinking of circumference. Thank you. Pi r squared. So since we're given diameter, the radius is half of that. So pi times half of the diameter, so 0.048. Because I was doing circumference instead of area. So when I find the area, I get this 7.24 times 10 to the negative third. You could certainly write that as 0.00724. That'd be fine. I'm just doing scientific notation, but you could do it whatever notation you want to do. Okay, so that's my area. I am going to go ahead and plug that in as normal notation standard, so 0.000 or 00724. Okay, now we get to delta B. So delta B is the change in the field. So the field started as 1.1, and then it says I removed it. Okay, I removed it from the field. That means the amount of field at the end is 0. So the change is final minus initial. So 0 minus 1.01. So the change in the field is 1.1. However, because I removed it, I decreased the field by 1.01. Yep. And then delta T is the time it took to do this, 1.5. And then it's just a matter of doing all the math here together. So this times the number of loops times negative 1.1 divided by 1.5. So we get an induced voltage of 0.265, and the unit is volts. You'll notice I ended up with a positive number because I decreased the field by 1.1, and Lenz's law states that it's always opposite. So if I decrease the field, I'm going to create a positive voltage here. Okay, so in what direction is the induced magnetic field? So I'm going to use this tape here to kind of represent my loop of wire. So how do I figure this out? So it says that the field is decreasing by 1.1 Teslas. So that means that the change in the field is out. Okay, so decreased is out, increased is in. So if the field is changing out, then the induced field is in. So what direction is the induced magnetic field? All you need to say for the direction of the field is either out or in, and the induced direction is in. Again, the reason I know the direction is in is from Lenz's law, I got a positive answer. That means the change needs to be inward, not outward. If I got a negative answer, the change would be outward.
Define inward.
Increased field through the wire. So the induced field is to create an increase even though the actual change is decreasing. So now we get to in what direction is the induced current in the wire. So here's how I figure out the direction. All right, so the change was to decrease. That's an out. The induced effect is opposite of that, so in. So I take my fingers and I curl them in. Okay, there's my fingers. They're going through. Remember, that's the direction of the field. Wrap your fingers because we know it's a circular path. And now my thumb is pointing in the direction. So I'm looking at this. I said the induced is in. Grab it. Stick your thumb on the edge. The induced current is clockwise because that's the direction my thumb is pointing. And that's the first right-hand rule if you're wondering where that came from. Okay? What happens if I was increasing the field? Well, if I increase the field, that's in. The induced field is always opposite, which is out. Put my fingers coming through out. Wrap them around. Stick my thumb on it. Counterclockwise. Which makes sense. If I'm doing the opposite effect, it should have the opposite direction. Okay? Now, I know these are tricky, especially the first time that you're doing them. So that's why we're going to make the practice fairly simple for today. There's only 2 problems for the practice, and that's on Schoology. You can find it on there. I have some copies if you need them. But there's going to be 2 questions for the practice, okay? The first one says a square coil of wire with the sides of 0.025 meters has 1,000 loops. It has a 0.6 Tesla magnet removed completely in 0.1 seconds. Okay? What's the induced EMF in the wire? What's the direction of the induced field? Again, a reminder, into or out is fine. And then what's the direction of the induced current, either clockwise or counterclockwise? Number 2 is a north pole magnet is inserted. Okay, 250 loops, has a radius of 0.1 meters. Again, circular coil here. This one is a square. I mentioned it. I said it incorrectly. This is a square one. And if you look at the bottom, here's your equations if you don't have them memorized. So there's the EMF equation. Okay, there's the area of a square and the area of a circle. So what you're going to do is I want you to work on practice 2. I'll put a submission online so that if you finish in class, you can go ahead and submit it. Okay? When you're done with practice 2, there is one more thing that you can work on, and it's practice 3. And I know you're saying, oh, so many practices. Well, let me show you what practice 3 looks like. A wire is carrying a current that's traveling into the paper. In what direction does the magnet field it produce act? Below the wire, to the right of the wire. This whole practice is nothing but directions. There's no math to do in this practice on practice 3. Okay? No math at all to do on that one. All of it is direction stuff. It's either the first right-hand rule, the second right-hand rule, or Lenz's law. But all it is direction. So here's what I want you to work on the rest of the period. I want you to finish practice 2 or get as close to being done with practice 2 as you can. Okay? If you finish, great. If you don't finish, that's fine too. But try to get as much done on that one as you can. Okay? If you get done with practice 2, then go on and start working on practice 3. But the homework for next time is just to finish practice 2. But if you get done early, you should move on to practice 3. We'll talk about practice 3 next time. But the more you can get done now, the more you can do review next class after that. Okay? So go ahead and work on practice 2. I'll give you a few minutes to get started. If you're having trouble getting it open on the computer, then let me know and I can give you a copy. Again, try to do these in your notebook if you can, or on a separate sheet of paper. That'll be easier for me to see, as well as easier for you to kind of draw and go from there. So that's what's due for next time, practice 2. If you get done with that, then move on to practice 3. So get started. I'll come around in just a minute, see what questions you all have.